Welcome. In the last lecture we discussed about basics of antennas. So, we looked into different types of antennas, but however we will see more detail today, and we also looked at the fundamentals of antennas, for example radiation pattern, half power beam width, first null beam width, side lobe levels and so on. And then we also looked at simple expressions for directivity, gain, as well as how to calculate reflection coefficient from the input impedance of the antenna, and then how to calculate VSWR. Today we will look at a very important parameter, what is a link budget. How do we really decide what should be the gain of the antenna, what should be the power transmitted, what should be the receiver sensitivity and so on. And then we will start looking all these antennas one by one. So, let us start with the link budget. So, a link requires a transmitting antenna. Let us say we have a transmitter, that transmitter is connected to the transmitting antenna, and then there is a receiver with the receiving antenna, and in between the transmitter and receiver the distance is r. And what we need to do it is, we need to find out if there is a certain power transmitter and what is the gain of the antenna, then what will be the received power. So, received power is given by this particular expression. When we start looking into more detail of antenna fundamental, we will see how this expression is derived, but just to tell you, the received power depends upon what is the transmitted power. So, higher the transmitted power, higher will be the received power, and if the gain of the transmit antenna or gain of the receive antenna, if they are large, then power received will be large. Now, one can see that it is proportional to lambda square. Lambda is C by F. So, that means it is inversely proportional to F square. Also, it is inversely proportional to square of R. That means, if the distance is, let us say, increased by 10 times, then the power received will be reduced by 100 times, or if the distance is doubled, then the power received will reduce by 4 times. So, this is a very important equation to design any given system. In fact, all the satellite communication, they start looking at that how much power should be transmitted, what will be the attenuation through the path, and also many a times when we design for a link budget, we always plan for minimum 10 dB gain margin. Okay. So, just think about when you are listening to the radio station, and these days we have this dish antennas, and if you are watching the TV, if it is raining, suddenly you see that the signal actually gets lost, and a cable signal comes there may be some problem in the connection and so on. Basically what happens, because of the heavy rain, the satellite signal which is coming down to the earth is getting absorbed by these water particles or getting diffracted by water molecules. So, that is why the power received by our receiver is reduced, and hence signal is not good. So, minimum general criteria is 10 dB gain margin. So, now let us just look at these basic antennas one by one. So, the simplest most antenna which we look at is a dipole antenna. A dipole antenna is right over here. Now, typically people start with the theory also, it starts with a very small dipole antenna, then we talk about a lambda by 2 antenna, and of course one can increase the length of the dipole antenna also. But this one here, the radiation pattern, if you see, it is actually radiating uniformly in all the direction. But if you start looking here, the maximum radiation is in this direction, and then as we go up, we actually see the very little of that. In fact, the dipole radiation pattern can be very simply realized by just thinking of this pen in my hand is like a dipole antenna, but please do not apply this to all different types of antenna. So, for example, if we look at a pen, if I look from the pen this side, I see the full length. If you see from your side, the pen is looking full side. Somebody is looking from this direction, it will also see the full length. But now, if someone moves from here, starts moving from here, goes to the top, what you really see now is just the tip of the antenna or the tip of the pen over here. So, when we go from here, maximum visibility or maximum radiation, as we move up we only see the projection. So, that means we will see lesser radiation or lesser intensity, and as we go up we will see 0 here. So, now maximum it is going to 0, and then same thing happens here. So, it actually makes a figure of 8. Now, this figure of 8 is getting rotated all around. So, it almost looks like a donut, but donut with a hole, not a continuous donut. So, a donut with the hole is what is the radiation pattern of a dipole antenna. Now, what are the different applications of dipole antenna? In fact, it is used in so many different things, but currently there is a one application where it is used very extensively, and these are RFID, that is a radio frequency identification. And that RFID, there is this chip is sitting there, and then what it has roughly about lambda by 4 distance on this side and roughly about lambda by 4 distance on this side. So, why we do the bending? Because the size is small. You might have seen that many of these RFIDs are fitted in the visiting card. So, in the visiting card you can see that the size is a big limitation. So, if we try to use a straight lambda by 2 dipole, it will be very long. So, what we do, instead of having this long dipole antenna, we bend it so that we can fit in the given credit card size. Now, the dipole antenna actually requires a differential feed over here. So, it requires 1 plus here and then minus here, which should feed these two elements. Now, there is another application which we have used. This is actually a very important application in a sense that we have used multiple things over here. So, this triangular shape has been used to obtain broad bandwidth, and these number of folds are used to increase the input impedance of the dipole antenna, and that is connected to a RF harvesting chip. So, it can actually harvest the signal. So, if you put a mobile phone next to it, it can generate a voltage, or if you take it next to the cell tower or Wi-Fi, it will actually generate the voltage. Now, instead of using a plus minus feed, which is known as a balance feed, here is an example where a coaxial feed is used. So, coaxial feed is known as unbalanced feed. Why? It has only a center pin and the outer periphery is grounded, whereas in the case of the dipole antenna it requires plus and minus. So, this plus is connected to this branch and the minus is connected to the other band. So, this is known as a balance feed, whereas simple feed which we had shown over here, here it is a coaxial feed. In fact, majority of the generators will just give us a single feed, and then we need to design a concept which is known as a balun, BALUN, that is known as balance to unbalance. So, here we have tried to achieve balance to unbalance using a microstrip version, and that is what is a microstrip line fed dipole antenna. So, as we go along in the course, we will see how to design all these antennas. Then let us just look at monopole antenna. Monopole antenna is nothing but half of the dipole antenna. So, one can see here this is the complete dipole antenna, but if we just draw the line in between here, if we make that plane grounded, and then this one is acting as an image. So, most of the derivation in the beginning we will see for infinite ground plane, that is for derivation point of view, and for infinite ground plane we can see the image current which is directly there. And so, if the monopole is a quarter wave, that means the current will be 0 here and current will go to maximum, and this is the image here which you will not be seeing it as such, it is just imaginary thing. But if it is a short monopole, then the current variation will be from 0 to triangular variation. Okay. The reason for that is quarter wavelength actually satisfies the complete boundary condition. This is an open circuit. So, at open circuit current will be 0. We are feeding it over here. So, this is the half wavelength and it is a sinusoidal waveform. Now, in practice there will never ever be a infinite ground plane. So, majority of the time we use finite ground plane. So, here is a monopole antenna and this is a circular ground plane which is used here, and this is the coaxial feed which is feeding the monopole antenna. Now, many a times this is also not possible, then what we do, we use an approximation of that. So, we actually use practically wires over here. In fact, for medium wave transmission, which I mentioned in the last lecture, medium wave transmitter at 1 megahertz would require an antenna of the height of 75 meter, and there we need to provide a ground plane. Now, earth may not be always a perfect ground plane, so lot of these radial lines are put on the ground, and these are long radial lines which have to be put. So, they will actually simulate the real ground plane. We have actually shown here one practical example also. So, here we have designed a broadband monopole antenna, and this one here is a RF harvesting circuit. So, what you can see here, that when this mobile phone makes a call, you can see that the antenna is placed at a certain distance, and the DC voltage which is generated over here is connected to the multimeter. You will be shocked to see that it actually generates about 6.7 volt. So, imagine what a mobile phone can do. It can actually generate such a high voltage. Okay. In fact, this voltage can be used even to charge a battery. So, it is a perfect example for RF harvesting application. Then we will look at loop antenna. So, loop antennas can have a very small loop diameter to a very large loop diameter. However, practically majority of the time loop antennas are used which have a small diameter. Now, this is shown here as a small circular loop. So, if we assume that the current is uniform over here, then this can be thought in a slightly different way. See, when we were looking at a dipole antenna, so we had a vertical dipole antenna, and where was the magnetic field? Magnetic field is around the dipole. So, if this is the dipole antenna, magnetic field will be like this here. So, that is what is known as omnidirection, and then the E field is like this, which was making a figure of 8. Okay. So, that is a directional antenna. Now, for the loop antenna, we can actually think reverse of that. So, loop antenna current is moving in a circular fashion. So, this can be thought about now, that this is equivalent to, instead of electric dipole, if it is a magnetic dipole, then this will be the field around that. So, approximation actually is valid, that instead of using an electric dipole, all we need to do it is we think of this as a magnetic dipole. So, this one, instead of becoming a magnetic field, now it is electric field. So, in fact, we can actually use this particular simple assumption, and that way we can find out the radiation pattern of a dipole antenna, and by using it interchangeability. So, whatever is valid for dipole antenna, so E field for loop antenna, it will become H field, and whatever is H field for dipole antenna will become E field. So, E and H fields are reversed. Now, one of the another interesting thing with the loop antenna is that instead of using a circular, one can use even a triangular or square. If it is small, radiation pattern is still given by the simple magnetic dipole equivalent to the electric dipole. Now, many a times multiple turn loop antennas are used also, because since it is a small loop antenna, it may have a very poor radiation characteristic as well as poor impedance, which we will see when we talk about more in detail about loop antenna. So, multiple turn antennas are used for better impedance matching, and lot of these figures I have taken from the Balanus book. A slot antenna is nothing but a complement of a dipole antenna. We had seen that the dipole antenna is nothing but a metallic thing here. Here I have shown a flat version. A dipole is, normally we look at a dipole as a circular rod, okay, or a circular wire. However, in printed dipole antenna, we just take a printed configuration. So, slot antenna is nothing but a complement of a dipole antenna. So, in principle, what we actually do in principle is that a slot is cut in the infinite ground plane. So, what dipole sees a metal, and then there is a air all around. Here what we have here is all the metal and you cut a slot in between. Okay. But now of course we also know you cannot have infinite ground plane. So majority of the time we have a finite ground plane and we cut a slot over here. Now this slot can be fed through this microstrip line over here. So what is a microstrip line? Actually speaking, it is a line which is printed on a, let us say, a PCB, printed circuit board. So on one side we have a ground plane with this particular slot, and on the other side we put this feed, and here we are feeding the antenna. So this current flows through over here. It actually sees an open circuit here. So current will be maxima here if this length is approximately lambda by 2. So the current is maxima here, that means the magnetic field will be around that, and that magnetic field gets coupled to the slot antenna. Now for slot antenna, the voltage currents are slightly different or opposite of the dipole antenna. See, in case of a dipole antenna, current is 0 here, current is 0 over here, current is maximum. Whereas for the slot antenna, voltage is 0 here because it is short circuit, voltage is maximum, and then voltage goes to 0 here. So current will be maxima here, current will be 0. Now you can see that if current is 0, impedance is given by voltage divided by current. So if voltage has a finite value, current is tending towards 0, this impedance becomes very large. So that is why instead of using a center fed slot antenna, many a times offset fed slot antenna is used, so that a proper impedance matching with, let us say, 50 ohm coaxial feed can be obtained. Then we will talk about linear and planar arrays and why we need arrays. So just to tell you, we have discussed about dipole antenna, monopole antenna, slot antenna and loop antenna. Majority of the time the gain of these antenna is just about 2 dB, or if you take a very large dipole antenna, it can be up to 3 to 4 to 5 dB. But what if we want a very large gain? And large gain is also associated with, let us say I want to send a signal from point A to point B. So what we need is we need a directional antenna, so which should radiate in this direction, and I need a directional antenna to receive this signal, or this signal can be radiating in all the direction. For example, let us say for FM radio, which is transmitting in all the direction. But however, if I use a directional FM radio, I can get a much better signal. However, majority of the time we don't use directional FM radio. There also we still use a omnidirectional thing. But however, if we use a directional antenna, one can get a much better quality, because you know that where is a FM transmitter. However, if we need a very high gain, then we can use arrays of these antennas. So for example, it shows here 1, 2, 3, 4 n element array. Now this is known as a linear antenna array because all the elements are placed in the linear fashion. Here is an example of a planar antenna array. I have shown an example of a rectangular planar array where m elements are placed in this axis and then n elements are placed in this axis, and that is getting replicated in this particular plane, which is xy plane. So the total number of elements will be m multiplied by n. So these are the number of elements. Now I have shown here just a planar rectangular array, but it can be square, it can be triangular, hexagonal, circular and so on and so forth. So the array performance depends upon so many factors. What kind of an element we have used. So in the beginning, when we start the array theory, we will use an isotropic element, and then we will take specific elements. Then it depends upon amplitude and phase of each element. So at what amplitude these elements are being fed, and what is the phase difference between all these elements. Just to tell you, when all these elements are fed with the same phase, it will radiate in the broadside direction, in this particular direction. And if the phase of each element changes, then the beam maxima which is in this direction, that can be scanned in the different direction. So phased array concept comes from here if we change the phases between different elements. It also depends upon the spacing between the elements. So, smaller the spacing for the same number of elements, total aperture will be small, so gain will be small. But larger spacing would mean that aperture area increases, the gain will increase. However, there is a limit, we cannot keep on increasing the spacing beyond certain limit. So, for now I can just say spacing has to be always less than lambda. Then it also depends upon the feed network, how these elements are being fed, because there may be a one common source, so that source may be dividing the power into different things. So, how we design the feed network. So, all these things govern performance of the antenna array. One more thing I want to mention here, that this linear antenna array can be generalized for continuous line source also. So, just think about if the spacing between the element is reduced, let us say this shows here d, if the spacing is reduced to say d by 10 and number of elements are increased by 10 times. So, the total aperture size may still remain same, but now the elements are very close to each other. So, here we can generalize, if d is tending towards 0, we can say that there is a continuous source. So, in fact, linear and planar antenna array concept will be used to explain all the different types of antennas. For example, microstrip antennas, they can be modeled as 2-slot antenna array, or we can think about a helical antenna, which is an axial mode helical antenna. We will see that it is a typical example of increased directivity end fire array. So, another example of, let us say, horn antenna. See, if I look at a simple pyramidal horn antenna of this shape, so what actually happens, E field is uniform in this direction and it varies sinusoidally in this particular direction. So, we have a uniform field in this direction and we have a cosine field distribution in this particular direction. So, array factor theory can be modified to find out the overall radiation pattern of horn antenna. Same thing can be applied even for a parabolic dish antenna. So, where the shape is parabolic, but the outer here is circular. So, over here again we can apply the array theory concept in this E plane as well as in H plane, and then we can find out what is the aperture distribution. So, array theory is very, very important to actually define most of the other aperture antennas. So, now let us just look at a microstrip antenna. It is one of the most promising antenna these days. Why it is very promising? Because the structure itself is so simple, one actually looks at it. So, there is a ground plane and a patch is printed on the other side. So, just like you are familiar with a printed circuit board PCBs, I mean it is there inside your mobile phone, inside any of your electronic gadget, you will see a PCB. If you have designed microcontrollers, so you know that there are multiple lines are going parallel to each other or perpendicular to each other, whereas a microstrip antenna is much simpler. So, all you do it is you take a PCB, we commonly call it a substrate, a dielectric material is there. So, on one side for a PCB it will be a copper and on the other side there is a copper. So, you do not etch out the copper underneath the thing, only we etch out the copper on the top side here. So, if this particular shape is a rectangular, it is known as rectangular microstrip antenna. If it is circular, it will be circular microstrip antenna, triangular microstrip antenna, or it can be hexagonal shape microstrip antenna, pentagon shape, sectoral, annular ring, and so on and so forth. So, now this antenna, actually you can see that this is the length and I have shown this as a width. So, this length should be approximately equal to lambda by 2, and if this length is approximately equal to lambda by 2, now you can see here this is an open circuit, this is an open circuit. So, current will be 0 here, current will be 0 there. So, the field will vary from here 0 current to the maximum current and goes to 0, because that is what is making half waveform. What about the voltage? Voltage will be maximum here, and then voltage will go to 0, and then voltage will go to the minus maxima. So it will start from plus, it will go slowly to 0, and then it will go to minus here. So if the voltage is maxima, current is 0. So impedance will be V divided by I. So impedance will be very high. Over here along the center line, voltage is 0, current is maximum. So impedance will be 0 here. So along this central one, the impedance will be 0 here, impedance will be maximum here. So then we can find a place where the impedance will be 50 ohm, and then we can feed with a coaxial feed. It is just one of the type of the feed. When we talk about microstrip antenna, we will talk about different types of feed there. And by choosing a proper feed point, then we will be able to match the impedance. So in fact, this particular configuration does not require any external impedance matching network. It does not require any balun which is balanced to unbalanced, and it is such a simple configuration. All you have is a just very thin printed circuit, and this printed circuit will have a very less weight, less volume. It can be bent around. In fact, there are printed lines are there. In fact, there are flexible PCBs are available which can be wrapped around a missile. It can be put underneath the aeroplane, it can be put inside a pager or a mobile phone. So microstrip antennas are gaining lot of advantages, and in fact in this particular course then we will talk about so many different types of microstrip antenna. We will start with the rectangle, but we will look at different shapes of the antenna. Then we will look at several configurations, how to increase the bandwidth of the antenna. We will also see how to make this antenna compact antenna. Then multi-band can be realized. We will also see how dual polarization can be achieved, that is horizontal or vertical. We will also see how circular polarization can be obtained, and then we will look at linear and planar array. We will look at different types of feed also, series feed, parallel feed, and even we will see how to use combination of the feed. So today in general we talked about simple principle of the link budget, which is very important to design a antenna system along with transmitter and receiver. It actually helps in determining what should be the transmitted power, what should be the receiver sensitivity, what will be the coverage, what are the gain requirements for transmit and receive antenna. And then we talked about a very basic antenna, which is we started with the dipole antenna, then we went to the monopole antenna, then we talked about a circular loop antenna, which is nothing but a small circular loop antenna, looks like a magnetic dipole antenna. Then we looked into slot antenna, which is nothing but the complement of the dipole antenna. So you cut a slot in the infinite ground plane, which is theoretically okay. Practically we cut it in a finite ground plane. We also just quickly looked into how to feed for proper impedance matching, and then we looked into microstrip antenna and why they are so popular. Because of the reason they are very easy to fabricate, and their weight is very small, volume is small, and the cost is also relatively small. They can be mass produced without any problem. And we will see what are the different things we can do for microstrip antenna, how to realize broadband, circularly polarized arrays, and so on and so forth. Thank you very much.